Okay. So, I have started recording. So, Ramna, stage to you.
Yeah, thanks for the kind introduction. I hope you guys are able to see my screen.
Yes, we can see.
Okay, so yeah, okay, we got the laser pointer too. So hello everyone. Let's discuss optimal control under uncertainties today. That's part of the lecture series. Here is a quick outline to my talk. Sorry, I'm hearing some.
Please mute yourself. If you are not mute, please mute yourself. Okay. So that will.
Okay, so yeah, here is a quick outline to my presentation. The most popular way of addressing planning under uncertainties is to have feedback controller. So we would first discuss what is open loop control, what is feedback control, the basics, and we try to understand what is the difference, why feedback even matter. And in search of feedback controller, we would first discuss the Hamilton-Jacobi-Bellman equation, which I think Professor Kothari had introduced in the last lecture. Then we would move on to deriving the linear quadratic regulator using Hamilton-Jacobi-Bellman equation. I know, again, Professor Kothari had a derivation explained in the last lecture, but this proof will be slightly different, and I hope it will give you more insights and a different perspective to understand LQR. So using both the Hamilton-Jacobi-Bellman equation and LQR, you would come at what is called the neighboring optimal control to essentially come up with feedback controllers around what is called the nominal trajectory or the nominal optimal trajectory. And with that, I would move on to discussing a little bit about stochastic LQR. It will be just one slide, trying to introduce the bare bones of stochastic optimal control. Finally, I wanted to have some sort of balance between fundamentals and more recent research that I'm also interested in, which is called the desensitized optimal control. I'll be discussing that at the final leg of this presentation. It deals with planning under parametric uncertainties. So this is a quick outline. So let's move on to discussing what is open loop and feedback. Oh, sorry. But before that, let's set some basic notation in place here. So T, as always, denote time, and x of t denotes state at time t, which is an n-dimensional vector, and u of t is a control at time t, which is an m-dimensional vector. So the basic optimal control problem contains a cost that you want to minimize using the optimal controller U star, and the cost has two components. One is the terminal cost, which is phi of x at tf comma tf, and tf here is the final time. That is called the terminal cost. And then you have what is called the running cost. It is integral t0 to tf L of xt ut comma t dt. So t naught here is the initial time, which in most cases is 0. So this form of cost is called a Bolza form of cost, which is more general, but you can always convert this Bolza form of cost to a complete alternate terminal cost function. And if you use such a cost function, it's called Myers cost, or alternatively, you can convert this entire cost function to just a running cost function into this integral form, which is called the Lagrange cost. Uh, Again, these two are different ways of writing the more general Bolza form, but we'll stick to the Bolza form of cost for the rest of the discussion that we have today. Okay, now that we have the cost, we have the constraints. The first set of constraints is the dynamics on the state, which is x dot is equal to f of x comma u comma t. And we assume that we already have the initial conditions with us, which is x at t naught is equal to x naught. So in the cases where the final time is not fixed, which is TF, you would have some sort of terminal condition that would tell when you would stop the optimization. The terminal condition could be anything. Let's say in a path planning problem, you want to reach the target. You don't have any final time fix, so which means that the moment you reach the target that is the terminal condition. So along with the terminal condition, you have what is called the trajectory constraints of the form g of x t u t comma t less than or equal to 0. So these set of constraints are typically inequality constraints, but there could be some equality constraints too. And these constraints would allow you to impose restrictions on the state space, or let's say imposing control constraints or control bounds. And this form of optimal control setup has been the backbone or the foundation of addressing planning in any sort of situations. For example, let's say simple path planning problem for a robot on ground to almost the most complicated system like hypersonic vehicle, again, understanding their entry, descent, landing, let's say aero capture of sorts. So now that we have the optimal control problem set up, we want to understand what is open loop versus feedback. So the idea is to obtain this optimal controller U star, but it is a function, it is an infinite dimensional object. You can have different ways of representing that function. What open loop control says is that the U star is a function of time, which means at every instant, give me the value of time, and I will give you the m dimensional control input that you have to pick to optimize the cost under those constraints. As opposed to what a feedback controller asks for is I need both the time and the state for figuring out the optimal control input. What is the difference? How does it matter? You may ask. So let's have a simple example. So in this example problem, the state and control are two-dimensional. And what this set of equations are trying to say is, imagine this situation where you have a circle with center xc and radius r. And the initial state is somewhere outside the circle at x naught. And the problem is to reach the surface of the circle in minimum time. That's what. So the cost is essentially the terminal time, which means you want to reduce this time by reaching the circle surface faster. And I'm assuming the dynamics to be a simple single integrator, which means I want to reach the circle by essentially controlling the direction of my velocity vector and the speed, which is the magnitude of the velocity. And I have essentially a bound on the magnitude of the velocity, which is u max. And again, as I said, since the terminal condition is to reach the circle surface, which means I can just express the condition in this form, which is the norm of the final state minus the center of the circle is within the distance r. Okay, now that you have this, what is the optimal control for this? We all know the optimal control looks in this form. What it says is draw the line between the initial state and the center, and that is the direction that you have to pick and max out on the maximum speed that you have in your disposition. Okay, so this is what this control is saying here. Again, xc minus x naught divided by norm of xc minus x naught is the direction, and u max is the maximum speed that you want to pick. Now at some time t, you are at xt. Okay, and then what is the controller you have to pick according to the open loop control? If it is u star of t, you pick u0. But what if at time t, instead of xt, you are at xt prime, slightly away from xt? Will you be picking the same control u0? Because that's what the open loop control would do. But we all know that is not the best you might do, and in this situation where if you're slightly away from the trajectory. The best control at this state is essentially, again, you draw the line and the direction changes. Of course, the max speed is going to be the constant, but since the direction is going to change, it's a different control. So now at some time t, if the state changes from what you had expected it to be at time t, then you have to change your control to be optimal according to the cost that you have, which is minimize the travel time. So if you want to automate this process, and if you want to have a general control that would give you the optimal control at every state that you would visit, then you would write in this form, which is a feedback form. So at a given state, you would choose ux, which is in this form. Instead of saying, I would pick this control regardless of what is the time, now I can write the controller in the function of both the state. And in this case, you don't need time because I think this is a stationary system, so the optimal control is not a function of time anymore. Okay, so that is the whole idea of feedback. Given any state, what is the best thing that I can do? Instead of just saying, I solve the problem given the initial conditions, but I don't care about what's going to happen in between the trajectory, because things don't go always the way you plan. For example, let's say you plan for a trajectory for a UAV, and there could be wind, gust, anything that just take it away from the trajectory that you had planned. But now you have to bring that UAV back to the ground by optimizing some cost function, which means at that time you have to have a feedback controller. So this is a simple problem. You were able to get the feedback control in this case pretty easily because you're just dealing with simple circles and simple dynamics. What if you have a general nonlinear optimal control problem? How do you arrive at a feedback control? And the answer is the Hamilton-Jacobi-Bellman equation. So in the past lecture, I think Professor Kothari had introduced the Hamiltonian adjoint equation, all this stuff, but let me quickly review these concepts once again before we get into the HJB equation. So given a standard optimal control problem, you would first write the Hamiltonian. The Hamiltonian is the summation of the integrand of the running cost, which is L of x comma u comma t, plus lambda transpose the dynamics, which is f of x comma u comma t. I'm dropping the time dependencies of the state and control for the sake of simplicity, but I hope you understand. So this lambda is called what is the co-state for this optimal control problem. And you can actually derive the dynamics for this co-state by essentially taking the partial of this Hamiltonian with regards to state and multiplying it with -1. And that is what is called the adjoint equation for this optimal control problem. Furthermore, you would arrive at the boundary conditions for the co-state and the Hamiltonian using, this is the terminal cost function, and this is the terminal condition for the optimal control problem. And here, nu is a multiplier. This is just standard procedure. I would just come up with whatever the parallels that you would see with a finite dimensional optimization in a second, but just, sorry, just be with me here for a second. So this is the boundary conditions you have for the co-state and Hamiltonian. Now, the optimality conditions are arrived at using what is called the Pontryagin's minimum principle. What the Pontryagin minimum principle says is that at every instant, the optimal control is the one that minimizes the Hamiltonian. So with that in mind, the first thing that you would do is take the derivative of the Hamiltonian with regards to u and equate it to 0. That would give you the set of candidate optimal controllers. And among the candidate optimal controllers, you would choose the thing that minimizes by essentially looking at the second order derivative of the Hamiltonian with regards to control and see if that is positive definite for that candidate controller. So these are just standard procedures, and this is the way you would probably obtain an optimal control under most conditions, assuming again the Hamiltonian is having double derivatives existing and unique. Okay, so with that, now if you want to arrive at the feedback control for this optimal control problem, the first thing that you would write is the value function. So the value function is again a function of the state at time t and the time, and it is in this form. What you see here is again the cost function, but slightly modified. What you have to understand here is you have the terminal cost, but instead of integrating the running cost from t0 to tf, you would have whatever is the current time. And that is why this is called cost to go. So which means at time t, what is the cost that I will incur from now on if I start with, let's say, some controller u of t. And the value function is the one with the minimum cost to go. So from that point onwards, if you choose the optimal control, you would incur what is the cost that is the part of the value function. So now if you define the value function, the HJB equation is essentially the partial differential equation that governs this value function, which is of this form. So which is partial of v with regards to t is equal to minimum u for L of x comma u comma t plus partial of v with regards to x, f of x comma u comma t. And notice that at the final time, the boundary condition on the value function is essentially the terminal cost itself, because at that time, there is no running cost, and the cost that you would incur at the final time is the terminal cost itself. So I'm not deriving the HJB equation because that is already done in the last lecture. And I don't want to come up with dense mathematical slides. So I just left it now for a second. But what I want you to focus on is this idea that both the co-state and the Hamiltonian capture some of the very important information related to the value function. So on the optimal trajectory, the corresponding co-state represents the sensitivity of the value function with regards to the state, and the Hamiltonian is essentially the negative of the sensitivity of the value function with regards to time. So why this is interesting, you can see it in this slide. So I hope you guys have already seen the standard finite dimensional optimization. So if you haven't, I mean, there is still a little bit of small introduction here in this slide, but I don't know if it does the justice, but bear with me. What we do in finite dimensional optimization is you are trying to minimize a cost, j, which is a function of x, and x is just an n-dimensional vector. And you want to minimize this cost subject to some equality constraint, which is c of x equal to 0. And I know, of course, I'm ignoring the standard inequality constraints, but let's stick to the equality constraints here for a second. And if you do that, the first thing you would do to solve this problem is you write the Lagrangian. The Lagrangian is, again, some j bar is equal to the summation of your cost function plus lambda transpose times your equality constraints. Here, the lambda is called Lagrange multiplier. And the optimality conditions for this finite dimensional optimization problem, which most of you guys have seen, I'm assuming, is again the partial of this Lagrangian with regards to this. I wouldn't call it state because here x is the parameters on which you're trying to optimize, because the moment you say state, you are assuming that there is some dynamics associated, but there are no dynamics. So I'm just calling it the design parameters. So the partial of the cost with respect to design parameters is equal to 0. And if you want the candidate minimizer to be the solution, then you have to check for that candidate minimizer, the second order derivative, and see if it is greater than 0. And this is what most of you guys already know, but very few people kind of notice or even make use of the fact that the Lagrange multiplier associated to this optimal function or optimal design parameter essentially captures what is the sensitivity of the cost function with regards to the change in the constraint value, which is very similar to what we had seen in an optimal control setting. Now draw the parallels here. So instead of Lagrangian, you have a Hamiltonian here. Here, again, you have the running cost function plus lambda transpose times, which is the dynamics. So the dynamics, again, is a constraint function on the state. So instead of what you call Lagrange multiplier in finite dimensional optimization, you call this lambda a co-state because it has an associated dynamics to itself, and the dynamics is obtained using the adjoint equation. And of course, you have associated boundary conditions through which you get from the transversality conditions. But again, if you see the optimality conditions, it's exactly the same. Instead of the Lagrangian, which is what you try to minimize, you are trying to minimize the Hamiltonian, and which is why you take the derivative of the Hamiltonian with regards to u equal to 0, and the second order derivative of the Hamiltonian with regards to u is greater than 0. Now, again, if you see the co-state here represents the sensitivity of the value function with regards to state, which is what exactly its counterpart in the finite dimensional optimization is kind of doing in a similar fashion. So this is a kind of comparative study that I wanted to mention because I think it's kind of very interesting, and this could be one of the potential research directions that one might take, which very few have actually explored. Okay, coming back to our question of how to obtain feedback controller, we have the Hamilton-Jacobi-Bellman equation. But to solve the Hamilton-Jacobi-Bellman equation and arriving at a value function that gives you a feedback controller, one of the popular ways is to use the method of characteristics, which is what you would use to solve a PDE. But the bottleneck here is you have what is called the curse of dimensionality for the Hamilton-Jacobi-Bellman equation, which means you have to have an enormous amount of storage required, even for some of the most simple problems, to solve the partial differential equation and arrive at a value function. I'm sorry. So what we do, we find an alternative. Instead of solving for a value function which captures the information regarding what you have to do over the entire state space, instead you would look at what is called the perturbation feedback scheme, or what is called the neighboring optimal control. The idea here is, given the original optimal control problem with the initial condition to be x naught and what are the terminal surface, you can solve the optimal control problem using, let's say, the traditional direct or indirect methods, which I think Professor Kotaria had introduced. But say that you have already a solver, an oracle that says, you give me the optimal control problem with all the conditions, and I will give you the open loop optimal control. That's what you are getting from that oracle. So if you have that, you can generate the trajectory here till you reach the terminal surface. What neighboring optimal control essentially does is that it linearizes the dynamics along this trajectory, and you create an approximate cost function over which you are trying to minimize about this nominal trajectory to arrive at what are called near optimal trajectories around this optimal or nominal trajectory, which means instead of focusing on the entire state space, you are focusing, let's say if I'm moving slightly away from this nominal trajectory by a certain amount, again, that amount is uh, quantified using some guarantees that you would get out of some assumptions, but with under small variations around this nominal trajectory, you can still talk about feedback control using this simple, or I would say, I shouldn't say it's simple because it's a very powerful idea what is the neighboring optimal control. So before we discuss neighboring optimal control using what are the HJB equation, the important aspect you need to know is the linear quadratic regulator. So again, I think you had seen this in the last lecture, but let me just brush up the basics for this. Here, the cost function is quadratic, which is you have the terminal cost function as of the form half of xf transpose qf xf, and xf here is the state at final time, and qf is typically a positive semi-definite matrix. And the running cost is again a quadratic form where you have half of integral t naught to tf x transpose qx plus u transpose ru dt. And here you mostly assume R to be a positive definite matrix, which you will see why in a second. And Q here is a positive semi-definite matrix. So this is the quadratic cost function you have for linear quadratic regulator. And the dynamics is linear, which is x dot equal to ax plus bu. And both a and b here could be functions of time. They need not be constant. And the theory works perfectly fine, even in the situation where a and b are functions of time. And you assume that you have initial condition given to you, which is x at t naught is equal to x naught. So following the standard procedure, given this cost function and this dynamics, and you assume no terminal conditions, and you assume actually that the TF is fixed. You have fixed terminal time, which means you don't have any terminal condition as such, and you don't have any trajectory constraints, so no bounds on control or no bounds on the state you can visit. So with that, you can simply write the Hamiltonian in this form, which is the integrand and the running cost, which is half of x transpose qx plus u transpose ru, plus the co-state times the dynamics, which is ax plus bu. Now you can quickly derive the adjoint equation, which is lambda dot is equal to minus of partial of h with regards to x, and you have to transpose it because you are following the row format for a partial a partial derivative of a scalar with respect to a vector, which gives you minus qx plus a transpose lambda. So in case you are slightly worried about how I got this, here is a quick cheat sheet for the matrix derivatives, which means if you have x transpose ay, and if you take the partial of this, essentially it's a scalar. If you take the partial of this scalar with regards to vector x, then you have y transpose a transpose as the derivative. But let's say if you take the derivative of this scalar with respect to y, then you have x transpose a as its derivative. And you use these two facts to arrive at what is called the quadratic cost function derivative, to which is if it is x transpose ax, and I'm sorry, it's a typo. If it is a partial with regards to x, then the derivative is x transpose times a plus a transpose. So using this cheat sheet, I can quickly derive the adjoint equations 2b minus qx plus a transpose lambda. And if using the transversality conditions, I can arrive at the boundary condition for the co-state at final time to be, again, partial of this terminal cost function with regards to xf, which means it is qf xf. Okay, so I got the adjoint equation, and now I want to get the candidate controller, which is the one where this derivative partial of h with regards to u is 0. So this is the Hamiltonian, and now instead of taking derivative with regards to x, I'm taking derivative with regards to u. And if I do that, I get Ru plus B transpose lambda is equal to 0, which means if I send this B transpose lambda to the other side and essentially multiply with R inverse on both sides, I get my candidate controller to be minus R inverse B transpose lambda. Okay, I got this candidate controller, but if I want to know if this controller is indeed the minimizer that I'm looking for, then essentially take the second order derivative, and you realize that that's when you see this R coming out, and you need this R to be positive definite for the second order condition to be valid to call this controller to be the optimal controller or the minimizer. So which is why I said in the beginning that R is typically assumed to be positive definite. If not, then you cannot talk about optimality for this controller anymore. And of course, if it is not, if it is, let's say, positive semi-definite, you cannot even talk about inverse existing. So you really require this R matrix to be positive definite. That's a requirement that you cannot compromise upon. Okay, so at this point, this is not a feedback controller. What you're doing is you're calling it a function of co-state, which means you have to solve the 2-point boundary value problem with state and co-state with these boundary conditions. And the moment you find the co-state, which will be a function of time, using that you would get what is called the open loop control with this equation. But if you want the feedback controller, what you do is, first of all, again, come up with the value function and the associated Hamilton-Jacobi-Bellman equation. So using the Hamilton-Jacobi-Bellman equation, the general Hamilton-Jacobi-Bellman equation, the previous slide, I can write the associated equation for this problem. Again, since the L is essentially the integrand of the running cost, I replace L with whatever the integrand cost I have, integrand of the running cost I have, which is half of X transpose QX plus U transpose RU. And notice that lambda is essentially the partial of the value function with regards to X. So I replace lambda with that, and I multiply it with AX plus BU, which is the dynamics. And again, as we already know, the value function of the terminal time is the terminal cost itself. And we have our optimal control to be minus R inverse B transpose lambda. And again, here you might want to replace lambda with the partial of V with regards to X. Once you do that, you can plug in this control in the Hamilton-Jacobi-Bellman equation. And if you do that, and you, with a little bit of algebra, again, trying to multiply U transpose in this form with RU and rewriting the equation, you would get minus of partial of V with regards to time is equal to half X transpose QX minus of half partial of V with regards to X, B, R inverse B transpose, and partial of V with regards to X transpose, plus partial of V with regards to X AX. So it's a mouthful, but it's very easy to derive this. You just have to, again, as I said, plug in minus R inverse B transpose partial of V with regards to X. That's because that's what is the co-state in this equation. That is all I'm doing here. Nothing complicated. The complicated stuff is yet to come. So if I do that, what I realize is for this partial differential equation, which is a function of X and time, the candidate value function will be of the form half of X transpose P of T times X. What is this P of T is something that we will be deriving in the next few minutes, but we know for a fact from the mathematicians, take my word, that the value function that would solve this partial differential equation is in this form, is a quadratic form with regards to X, and the P is essentially a function of time. Okay, if you know that this is the form of the solution and you want to figure out P of T, the first thing you would do is, again, take the derivative of this value function with regards to X to talk about the co-state, which will be of the form Px, which means the co-state is essentially a linear transformation of the state with P as the matrix. Okay, you have this. Now simply just plug in this value function in this Hamilton-Jacobi-Bellman equation. If you do that, the partial of V with regards to T will become half of x transpose p dot of x. Notice that x is not a function of time here anymore. I'm talking x is a free variable like t, which means I just have to take the derivative of p alone. I don't have any derivative for x, which most people might get confused because we say x dot equal to f of x comma u comma t, and if I take the derivative of this, people might end up using chain rule, and that is a very standard or a very general mistake people might do. But x is an independent variable like time in this value function case. So be aware of that when you're trying to derive this equation if you're doing it by yourself. And okay, so you have minus of half of x transpose p dot x, which is equal to whatever x transpose qx, that is what we have here. And we know partial of with regards to x is px, which means you have minus of half of x transpose p, b r inverse b transpose px, plus again you have partial of with regards to x, which is again x transpose p times ax. So I just plugged in the value function and its derivative in the Hamilton-Jacobi-Bellman equation. And now I will play a little trick, which is notice that this x transpose PAX is a scalar, which means if I take a transpose of this, it's not going to change its value. So which means I can rewrite this term in this form, which is x transpose A transpose PX plus x transpose PAX, which means I took the transpose, I added it, and I just divided it with 2. Okay, this is a trick that you would, this is the only trick I am playing, I would play in this entire derivation, but I hope you guys are still with me. If you have any questions, you can stop me here, because anything that's gonna come in the next slide will be based on whatever we had discussed in this slide, which is very important. And I'll give 30 seconds to 1 minute for you to respond. Any questions up till now, or did I go really fast? Okay, I don't see any chat. Professor Kotar, any questions on the chat? No?
No, it's all right. So you can.
Okay, cool. Awesome. So I'm assuming everyone is on the same
So
page.
Ramana, there is a question on P is a symmetric matrix.
Oh yeah, yes. Yeah, I'm sorry. I think I've forgot to mention that. Yes, P of T is a symmetric matrix. Exactly, which is why when you take the transpose, you are just taking P transpose to be P. Yes, that's a good catch. Yeah. Yes. So yeah, I think I forgot to mention that the value function should be a positive definite function. Why? Because first of all of this, sorry, I think, okay, let me just go back a slide. So if you realize all of these are either positive semi-definite, these two, and this is positive definite, which means if you actually calculate the value function, it should be positive semi-definite at least for all time, which means you want this P of T to be positive semi-definite, which is why if you take x transpose pt of x, this becomes a positive semi-definite scalar, which means this is a symmetric matrix. Yes. Okay, so I am, looks like everyone is on the same page. So moving on, I just took the previous equation and I'm just writing it here. Now the idea is just bring all the terms on the right side to the left side first, and essentially take x transpose on the left side and x on the right side common, and separate whatever we have, which is half of x transpose times p dot plus A transpose P, which is here, plus PA plus Q minus PB R minus B transpose P, which is equal to 0. So this is what we have right now. And at this point, if you want to know the solution for this equation, the trivial solution is x equal to 0. But you want this equation to hold for all time, which is what we are trying to say. We have the value function, and you got the Hamilton-Jacobi-Bellman equation. Sorry, you got this equation from the Hamilton-Jacobi-Bellman equation, which is valid for all time, which means for it to be 0 for all time, the only way that is possible is if this thing that is inside the parenthesis is 0, which is the non-trivial solution. And if you do that, you get the dynamics for your positive semi-definite matrix, which is P dot is equal to minus A transpose P plus PA plus Q minus PB R inverse B transpose P, which is called the famous differential Riccati equation. And now you can define, or you can arrive at the terminal condition for the P matrix, which is again partial of V with regards to X is QF XF, and if you equate it to PF P of P at TF times XF, you get P at TF is equal to QF. And with that, you can actually define a feedback controller for the LQR problem, which is U star is equal to minus R inverse B transpose PX, and you get P from by solving this dynamical equation. Okay, any questions?
There is a question.
Oh, okay.
But PA is not symmetric. The previous slide you go.
Oh, I see.
So, yes, see what you have done. See X transpose PA. So he get confused. There is a Jitender because you have told the scalar, right? So he's telling
Right.
PA is not a symmetric.
But what we are doing is we are taking the transpose of this entire value, which is if you take X transpose PA X whole transpose, then you get X transpose A transpose P transpose X.
So,
but you know P transpose is P, so which means you get X transpose A transpose PX.
So what Ramna is telling, that see any matrix A is there, symmetric component you can write A transpose, and since P is already symmetric, you write PA plus P A transpose P, that will be a symmetric component.
Yeah, I mean, I think a blackboard would really help with this sort of lectures, but yeah, I'm limited by just presenting slides. I think maybe I should get an iPad soon and probably start writing when I'm presenting.
See, we can write A plus A transpose
Yeah.
is symmetric component, and A minus A transpose is a anti-symmetric component. So
yes, yeah.
So basically, you have written the A transpose. Only P is now A is not A. That is a PA. Okay.
Right. Yeah. Oh, I see. Okay.
Hmm.
Right. I understand. Okay. I see
Hmm.
what he's trying to say here.
Hmm. So.
Okay.
Oh.
So
Hmm.
going back,
Hmm.
sorry. Anyway, so you have obtained the feedback controller for the LQR problem in this form. Now using this, we can arrive at what is called the neighboring optimal control problem, which is essentially the first thing you would do is you arrive at the augmented cost function, which I think Professor Kotari had introduced in the last lecture. I'm taking most of his content. So J bar is equal to your terminal cost plus your multiplier times your terminal condition plus integral T naught to TF Hamiltonian minus lambda transpose X dot dt. So if with that augmented cost function, if you want to arrive at neighboring optimal control, what you would first do is essentially you assume perturbations in the initial condition and and the terminal condition to be of the form delta x naught and delta psi. And if you assume perturbations in those initial conditions and terminal condition, you are expected to face perturbations in the state, co-state, control, and the multiplier, which means if you want to figure out what are the second order variations in cost, there will be functions of all these variations, and it can be written in this form. Again, I'm not going into the derivation, but I simply want you to focus on the fact that this exactly looks like the quadratic cost function that we had seen in the LQR format, right? So you have X transpose, this is essentially the QF you had seen in the previous slide, times XF, and which means QF is essentially the second order derivatives of your terminal cost and the terminal condition, plus whatever is the integral cost function you have, which is now, instead of whatever the quadratic cost terms you have X transpose QX plus U transpose RU, you have X transpose HX X plus U transpose HU U. But along with that, you also have some cross terms, which is of the form X transpose HUX U plus U transpose HXU U. So this is slightly an extension to whatever the standard optimal LQR problem you have. But if you accept this form and you essentially try to linearize the nonlinear dynamics about the nominal solution that you had got, let's say from some controller, from some oracle, and you can take the linearized form for even the terminal condition, you can solve this problem using the LQR format. And the solution will be of this form. So this is exactly minus R inverse B transpose lambda. And since you have the cross terms, you have to add this extra term, which you can derive using the stuff that we had discussed till now, but with slight modifications. And it shouldn't be a big deal. Trust me. It's if you understand the derivation that we had gone through in the previous slides, adding this extra cross terms is not going to change a lot. So, but this solution is again in the form of the state and co-state. But you want to get to this format where we call this a neighboring optimal feedback law, where delta x is the feedback state that you are getting, and delta psi is already something that you know is the terminal condition perturbation that is given to you. So you can completely change or essentially rewrite the open loop feedback control form using some algebra to arrive at this form, where you have delta u is equal to lambda 1 at time t times delta x plus lambda 2 at time t plus at delta psi. And you get this lambda 1 at t and lambda 2 at t using the nominal trajectory that you get. Those are just the functions of the states and control that you would see for the nominal trajectory, which means you already know that. And you just have to know what is the error in the state you get through your feedback, and then essentially correct the control by delta u. So this is a kind of a simpler way of arriving at feedback controller without going through solving the partial differential equation, by just simply uh, linearize the system along the nominal trajectory, take the quadratic cost function using the Hamiltonian derivatives, and arrive at the feedback law. I
So,
mean, I know for a fact I had skipped a
Ramna,
lot
I
of
have a
important
question.
information, but yeah, I'm sorry, sir. Please.
So basically, what you are doing, see, you taking the perturbations. So for all perturbations, so instead of drawing like you can forcefully x goes to x star, where x star is my optimal trajectory. So this the second variations gives the new LQR problem, right?
Right, exactly.
And with this new LQR problem or LQR type problem, you have come with the computation of delta U, right?
Exactly, yes.
Okay. Okay. Mhm, mhm, mhm.
Okay, so sorry. I mean, you can see the moment you understand LQR, neighboring optimal control is just an application of LQR to arrive at feedback controllers for general nonlinear optimal control problems around the nominal trajectory. Okay, so I felt like I can quickly introduce, since we had discussed LQR, essentially LQR in the stochastic settings, which means now you have some noise sitting in the dynamics, and the state becomes a random variable, which means you can only talk about expectations of the state, or let's say expectations or the first, the moments of state, which is the random variable. So given the dynamics of the form x dot is equal to ax plus bu plus w, and you know for a fact the initial conditions is x at t naught, but then since it's a random variable, you have to talk about mean and covariance. In this case, you can take expectation of x at t naught equal to 0, and the covariance is, let's say, cap x naught. And you assume this noise to be Gaussian white noise, which means the expectation of this W is 0, and you assume that the noise is uncorrelated over the time at between any two times, which means you can explain that in this fashion, where expectation of W at t times W transpose at tau is equal to whatever some matrix, which is a function of time. And this is what is called Dirac delta function, which means if t is not equal to tau, this becomes 0, which means the expectation of W at t times W transpose at tau is equal to 0. And since you have random variables sitting in the cost, you can only talk about expected cost function, which is what you can minimize. And even for this problem, which is essentially an extension of LQR in the stochastic realm, the optimal feedback controller doesn't change, which is very interesting. And you can actually derive this using standard stochastic optimal control techniques, or even using deterministic control with some tricks. But I really want you to appreciate this idea that regardless of whether the noise is some noise or let's say it's the Gaussian noise, the feedback controller is not going to change. It's going to be of the form U transpose equal to minus kx, where k is equal to R inverse B transpose P obtained using the differential Riccati equation.
Only so only Ramna, only thing is that now this X is a min. See, it's a min optimal control problem, right?
Yes, I mean, yeah, exactly.
X is
That's the
replaced by
best you
its
can do
min
for the
value.
stochastic systems, yes.
Mm-hmm. So this problem is divided into two part, mean and covariance steering, right?
Yeah.
Okay.
And now you can talk about, since you can only talk about average trajectory or variation around the average trajectory, you can talk about covariance in this case, where now the covariance at time t for the state is essentially expectation of xt times x transpose of t, and you can derive the covariance evolution using the control that you had obtained and plugging it back into the control and taking a derivative of this equation, and it is of this form, which is x transpose equal to a minus bk times x plus x times a minus bk transpose plus w. And this w is the same w we are seeing here in this equation. And the initial condition on the covariance is essentially x naught, which is also already given. So the moment you, okay, so Satyanarayan is asking, is the system linear time invariant? Actually, it doesn't have to be invariant. It could be time varying, but the system is linear. Yes. You need. I mean, I'm only dealing with linear systems at this point. Anything that you have to deal with non-linear, you can only either follow the tricks that you get from the linear control, or it becomes very subjective depending on the structure of the problem and everything. So it's hard to arrive at general non-linear optimal control solutions. So again, this equation is at some level a form of differential Riccati equation, which you would see in the Kalman filter, in the Kalman filter theory. So I just want to again, make you realize that the covariance evolution that you see and the differential Riccati equation that you see are indeed related, and they are exactly the same in the case of the dual problem, which is the estimation problem. Okay, so with that, I'm closing the topics related to stochastic control or whatever the neighboring optimal control, and moving on to the more recent research that I am pursuing, which is planning under parametric uncertainties. So I think I have roughly 10 minutes, Professor Kotari.
Yes, you can discuss 10 minutes.
Yeah, okay, cool. So let me quickly motivate the problem, because I mean, in most cases, people go for stochastic uncertainties, and especially in path planning, we have a lot of approaches concerned with stochastic uncertainties, where you use Gaussian processes, form DPs, occupancy grids, everything. But what I'm doing here is essentially I'm assuming the uncertainty to be parametric of nature. Instead of having Gaussian noise or any sort of uncertainty that is of stochastic in the estimation or in the process, I'm assuming that the model parameters, which essentially define the dynamics of the state, to be having some nominal values, but those values can change by a certain amount around that nominal value. So which means the moment you assume the uncertainties to be parametric, you can, instead of going to stochastic optimal control, you can deal with planning just with the deterministic approaches, and which is what you will see in the next few slides. And you would use this sort of planning approach for cases where there are limited sensing or feedback capabilities. Because in the past, we had just discussed, sorry. Okay. So in the past, we had discussed whatever is the feedback control, but in most cases, if the uncertainties are really bad, feedback control can only do so much. Let's say, regardless of how bad are your uncertainties, feedback controller can only I mean, typically have some limitation. Let's say you can have input saturations, or let's say you can have really high amount of feedback that could be detrimental to the system. For example, let's say in the case of an airplane, you can have feedback by using control surfaces, but beyond certain amount of weather conditions, the control surfaces can only correct you by so much. And using the high amount of feedback control can also break the system, which is why you might want to actually rewire the nominal about which you are actually calculating the feedback control under these uncertainties, which is the idea of what is called safe open loop trajectories. So how do we capture the effect of parametric variations on system's trajectory? So forget about optimal control for a second and see the dynamics here, which is x dot equal to f of x comma u comma t. Now we have the model parameters added. These parameters, for example, could be, let's say, gravity or aerodynamic coefficients, which we know have some value, but it need not be exact. So what the value we know is what I call P naught, and that is the nominal value. And we assume P will assume uncertainties around this P naught. Okay, so now if you have this dynamics, how do we capture parametric variations? Or the effect of parametric variations. So let's say you have the initial condition x naught at t naught, and if you plug in p equal to p naught, and for some control, you can derive what is called the nominal trajectory by propagating this dynamics. But let's say if you have p naught plus delta p, and you assume some that variation delta p, and you again plug in this equation and propagate the dynamics, you get what is called the perturbed trajectory. So now at time t, you can look at what is the variation in the state, and you can call, okay, this is the effect of parametric variation on the state at this time t. But if you want to automate this process, you just use Taylor series expansion. You take first order derivatives of the state with regards to of the state, which is a function of now the time and the parameter, and you take the derivatives with respect to parameter and then multiply it with the variations of the parameter to essentially capture what is the variation in the state. But in most cases, you just approximate it with variations of first order, and you can approximate delta x to be partial of x with regards to p times delta p. And you call this partial to be what is called the sensitivity function. And the idea is you can derive the dynamics of the sensitivity function, which is actually linear, which is x dot is equal to as plus b and s at t naught equal to 0. And the a and b matrices are essentially the Jacobian of the dynamics with regards to x and p evaluated along the nominal trajectory. And one quick thing that I want you to focus is the initial conditions of the sensitivity is 0, because you're already given the initial state to be x naught, which won't have any variations under any parameter variations. So which means partial of x naught equal to p equal to 0, which gives you s at t naught equal to 0. Okay, this is called actually the sensitivity equation in the literature, and you can see this in Khalil. If you've already read it, it's very nice book on nonlinear systems, which you should read at some point of time if you're pursuing controls. And it's called sensitivity equation. So now that we have the dynamics for the sensitivity function, how do we utilize these sensitivity functions? The first idea is what is called sensitivity regularization. So right now we have our standard optimal control problem with P naught being the nominal value of the parameter. And I call this the original optimal control formulation under nominal conditions. So if you solve, again, using any off-the-shelf solvers and some oracle that gives you the nominal trajectory, if you assume variations in the parameter, you would have dispersion about this nominal trajectory. The idea of sensitivity regularization is essentially to penalize the sensitivities or the norm of the sensitivities by using, let's say, a terminal cost function, the running cost function, and augment the sensitivity dynamics to your model along the initial conditions. And you're assumed or you're guaranteed to reduce the dispersion by a certain amount, depending on how much you penalize the sensitivity cost. And I call this the modified optimal control formulation under normal conditions. So in this case, I'm just changing the nominal. Again, at every time, I'm not coming up with any feedback control, because you can arrive at feedback control using the neighboring optimal control. But here, the problem is, can I come up with better nominal control solutions for adverse uncertainties? So one way is, again, you penalize the sensitivity cost, and that would reduce the variations by itself, even if you use open loop control, which means the feedback control will have less pressure. Okay, one simple example is this idea of a Zermelos navigation problem, where let's say there is a boat at the origin and the x1 axis is the shore. And if you go along the x2 axis, you are going into a river where the flow increases as you move away from the shore linearly. And you want to reach this 2, 0 on the shore in minimum time. And the idea is the flow is actually along the positive x1 axis, which means you can use the flow to reach here faster, but the flow can become uncertain as you go away from the shore. So I'm simply writing this scenario in the form of mathematical equation saying x dot equal to cosine u plus px2 and x2 dot equal to sine u. And p here is the parameter that talks about what is the intensity of the flow, I mean, as you move along the x2 axis, which I assume is uncertain. So if I use the previous technique, which is a sensitivity reduction technique, and if I start increasing the penalty on the sensitivity cost, I get this series of trajectories. And alpha equal to 0 is where there is no penalty, and this is whatever is the nominal trajectory that you would get without any desensitization is what I call. But the moment you keep increasing the penalty by essentially changing this parameter alpha, you would realize that the trajectory is moving closer to the shore, which means it's trying to balance between reaching there faster and addressing uncertainties in the flow. And here is the Pareto frontier that you can look at. So as you keep increasing the penalty, the sensitivity in the state is reducing and the time is increasing, which means you are having a trade-off between whatever the dispersion that you can arrive at, the dispersion in the final state versus the time that you would take to reach the final state. And here is the Monte Carlo simulations where you would realize that as you keep increasing penalty, again, the variation in the state is getting reduced. And at the final state, you are getting more and more precise to reach 2, 0. This is another example, I think more relevant to aerospace people, where in this situation, I'm actually trying to plan a trajectory for a hypersonic vehicle that is entering the atmosphere somewhere on the Pacific, and it wants to reach the Kennedy Space Center in minimum time. But apart from reaching the Kennedy Space Center minimum time, I'm concerned about the error in the final position and also the error in the final energy. If you are an aerospace engineer, you know that how much energy variations are very important. For example, even in the fighter jet maneuvers, it's well known that you have to maintain the same energy level, which means you don't want any variations around the current energy that you have. So with that kind of motivation, I'm trying to reduce variations in the final position and energy while I'm trying to minimize time using whatever technique I had presented earlier. And the baseline talks about the situation where I have no sensitivity cost, and desensitize is where I have some penalty on the sensitivity cost. And you can quickly realize that the error ellipse is reducing from 53 kilometers to just 7 kilometers. And at the same time, you're also seeing the situation where the energy is now becoming more and more prominent about the nominal value, which means the error is getting reduced. So these are like some of the applications that I've looked into using what is called a desensitized optimal control. And with that, I finish my presentation, and I'm open to questions. I'm sorry, I think I went slightly over the time that I was allotted. Sorry about that.
Thanks. That's all right. Very interesting. So, I'll stop recording and then we'll take the questions. Okay.
Yeah, sure.